So let me begin by recalling the two main constructions in my talks. One of them is a more basic one. So let's say x over k is a k scheme. Now I have been a little bit maybe not very careful when you need a variety and when you need a scheme. The thumb rule is whenever I am talking about Cartier divisors, because Fulton is not talking about meromorphic functions as Nitin explained, so there any discussion on Cartier divisors is on a variety. But if you are having a pseudo divisor, basically line bundle and section and all that can be done over a scheme. So what we have done is given a scheme and D a pseudo divisor, let's say D equal to L comma Z comma S. So this is a pseudo divisor. Then we have this D dot alpha, this construction. So where alpha, so for alpha in let's say AK of X, we have this D dot alpha. This was one of the main constructions in my lecture, and it makes sense as a class in AK minus 1 of X, but a little bit more. So this more will be used today. It actually makes sense as a class in AK minus 1 of support of D. In fact, I can further reduce it, support of D intersection support of alpha. But what we will use today is this support of D. So this class is defined here. And why is it defined here? You will have to go to the definition. So basically, the point is I can assume alpha equal to V. Okay, so this is the standard reduction, and then and let's say J is the inclusion from V to X. Is my handwriting too small or is it readable? Darker. Okay. So if J is the inclusion from V to X, then D dot V, we define it to be J upper star D and a square bracket. So this is the thing to revise and recall, even if you postpone understanding the proof that this D dot alpha takes rationally equivalent classes to rationally equivalent, that is later, but it's important to understand the definitions first. So this what is J upper star D? I pull back the line bundle and Z comma S. It may happen that the inverse image of Z is the whole of V. In that case, I just have a line bundle, and then there is this main trick, line bundle trick, because you see, how do you intersect with divisors if something is already in the divisors? We don't know. So we convert divisor to line bundle and then pull back the line bundle, and then line bundle to divisor up to rational equivalence. This is okay. So this is the main trick to intersecting with divisors. So then here, if for example Z inverse J inverse of Z is not the whole of V, then I actually have a meromorphic section of the pullback line bundle. I actually get a well-defined cycle class. If not, then I have a line bundle, and I get I can up to rational equivalence I can get a codimension 1 cycle. But then here is an opportunity to understand that whatever this construction, either V is contained in the support of D. In that case, you are cooking up a cycle on V, so everything is happening in support of D. Or if V is not contained in support of D, then inverse image of Z is not the whole of D, and then I actually have a well-defined divisor which is contained in the support of D. So no matter what, this is well defined as a class in AK minus 1 of support of D. Okay, so I won't be using this intersect even smaller thing, but it is a well defined class in support of D. We use this to define the Gisin homomorphism, or the pullback to the divisor, as Nitin said, like pullback by a morphism which is of relative, you can think of it as relative dimension minus 1. So now so this is the main construction, and then using this we define churn classes. Okay, so if E is a rank E, or let's say rank I hope I get the indices right. So rank, let's say E plus 1 dimensional, rank E plus 1 vector bundle on X. Then I construct this proj of E, and I have this map pi to X, and then first we define the Segre classes Si of Si. This will be an operator from ak of X to ak minus I of X. And how is it defined? Si of alpha is equal to, you pull back alpha, you take cup product with C1 of O1 to the power E plus I. Now you can correct me if the rank should be E plus 1 or E plus 1. Okay, so you take cup product with E plus I, and then you push forward this thing. Okay, so this was the definition of Segre classes. A priori it can live in all degrees. So of course this I should, strictly speaking, I should write Si of E, because it's a Segre class of this vector bundle. Now the vector bundle is fixed, so I'm just calling it as Si. Okay, so now we observed one thing about this Segre class, that S naught of E is 1. So basically it's the identity operator. So S naught of, or let me just say that S naught cap alpha is just alpha itself for every alpha. So S naught equal to 1. So that is S naught cap alpha equal to alpha. So this is for all k cycles. This is what we proved. How did we prove this? If you remember, we reduced it. Of course, there are only two explicit calculations you can actually perform. One is with the fundamental class where there is no rational equivalence, and one sometimes with the divisor. Okay, so in this case we reduce it to the case. So how let's recall how we proved this. So alpha, so without loss of generality, alpha is the fundamental class of a variety, and then you assume x equal to v. Okay, so now we are in the variety case, and then then you see this thing was C1 of O1. So, and we also, yeah, so we observed that S naught of S naught cap alpha is actually some m times x. This is what we observed. And then we also observed, that time we did not have this push-pull language, but we sort of in an ad hoc manner we used it at that time, and we said, okay, restricting to open set will give me the same integer, because inverse image, and so there you can formalize now, use that push-pull, and so I can restrict it to the an open set and calculate this integer. So basically reduce to the case where E is trivial. So in that case, my proj of E is actually x cross PE, okay, and now my alpha is of course square bracket x, and then this boils down to saying that if I look at C1 of O1 on this x cross PE, then that to the power E, okay, cap with the fundamental class, and then push forward with pi. This is equal to x, square bracket x. So the m is equal to 1. Okay, I am deliberately, I have made it a bit more complicated by writing this cap with, because I want to say something more, but I am hoping that you understand this. So if I take the top churn class and its eth power, basically I have to keep on intersecting it with the hyperplane. Hyperplane is the divisor corresponding to C1 of O1. Then finally I get a point, so I get x cross 0 as a cycle when I take this cap product, and x cross 0 pi lower star, I get the cycle x, right? Now this same proof I would like you to modify and show this, show that SI equal to 0 for I less than 0. Let's do this verbally, but you can work out the details. What happens is, if I is less than 0, then I am capping with an integer which is less than E, right? So what will be the dimension of this cycle? it will be more than the dimension of X, because each time I cap with C1 of O1, I cut down the dimension of that cycle by 1, right? And so C1 of O1, so if I raise C1 to the power, some power which is less than E, then this whole thing is represented by a cycle which is of dimension, every component, in fact it's an irreducible, you can cycle, so it's of dimension greater than dimension of X, so its push forward will be 0, right? So that is, so this is let me not write down the details. So so this is an exercise, all the negative Segre classes are 0, so say similar calculation. Okay, so now once we have this Segre classes, we define Chern classes. Okay, so we defined Ci of E, or simply Ci. So when the vector bundle is fixed, I'll just use the word Ci to formally satisfy this relation 1 plus C1 T, T is some variable, maybe I should write capital T, C2 T plus dot 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 times 1 plus S1 T. 1 is this S0, so I'm omitting S0, plus S2 T plus dot dot dot. This is the total Segre class, and this is the total Chern class that we have to define, and we want this property, that formally this should be the inverse of this. And if this is bothering you, you can write down formulas. C1 is minus S1 and Cn is equal to minus of S1 Cn minus 1. You have to define this inductively, so plus dot 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 up to Sn. Okay, so there, if this is but this is very convenient for convenient formulation. So anyway, this is the explicit description of Chern classes. They are operators. Okay, so what is multiplication of operators? You compose the operators. So that is. So now we want to prove this is not really analogous to the Chern classes we saw in topology. In topology, we saw that the Chern class satisfied this polynomial. If zeta was the class of O1, then we zeta to the power rank plus 1 was an expression of lower powers of zeta, and the coefficients were Chern classes, right? So arranged properly. So we will prove a similar thing for this. Oh yes. So why do SIs and CJs commute? So this is because of see, in general our we have proved this d dot d prime is d prime dot d. So whenever I am taking dot product with a pseudo divisor or a line bundle, then the order of taking that dot product does not matter. Okay, so the Segre class of any vector bundle, ith Segre class of E and jth Segre class of any other vector bundle, they are going to commute, because they on some bigger space they will be Chern classes of line bundles iterated. So that commutativity I am going to leave it for you to check using d dot d prime equal to d prime dot d. Finally everything is defined as using some divisor cross alpha. So they do commute. So all the SIs commute, for example. Okay, so now the main theorem which we want to prove. Okay, so yeah, but why do the SIs commute? And in fact, not just the SIs commute, SI of E will commute with Sj of F, like any two. Correct. For here I don't need, but that's a property like that we have. So okay, so this is the theorem we want, theorem 3.2. So for all E, now X is any scheme. So first property we have, so E is rank, E is a vector bundle on X, and we want to prove these list of properties. So first is that Ci of E equal to 0 if I is greater than the rank of E. Okay, this is not at all obvious. Okay, so because for Segre classes okay, negative are 0 and S naught is, we cannot, there is no like quick way to see what is happening to top Segre classes, and so this is at least not clear to me immediately, but we will prove this. And B, this is the property that Nitin just said. So commutativity Ci of E dot Cj of F equal to Cj of F dot Ci of E. Okay, so some properties I am going to leave it for you as an exercise. This is one of them. Okay, so exercise, use this d dot d prime, and you'll have to go through the this push forward and the definition. So therefore showing this is actually a good exercise, because you'll have to work with two projective bundles and maybe take further fiber product work over there. So anyway, in any case, so this is something I'm going to leave for you. The first, of course, is not obvious, so that we will do. So C is projection formula. So F from x prime to x is a proper map. Then F lower star of C1 of, or Ci of E cap alpha, sorry, I have to take the pullback of E, Ci of F upper star E cap alpha is equal to Ci of E cap F lower star of alpha. Okay, so if I, and of course, where is alpha? Alpha is a class on x prime, so alpha is in is a class in on x prime. So if I push forward a class and operate the ith churn class of a vector bundle, that is the same as pull back the vector bundle, take the ith churn class, operate it, and then push forward the result. So projection formula. This also I am going to leave as an exercise, because the main, it follows from projection formula for this operation d dot alpha. Okay, that we did, because finally the churn classes they are defined. So you can first prove this for Segre classes, for example, where the definition is a bit more explicit, and then for churn classes it will follow. So this is also an exercise, because it follows from the projection formula for d dot alpha. So okay, so next is commutativity with respect to flat so functoriality with respect to flat pullbacks D. So if x prime, so F from x prime to x is a flat morphism, okay, then F upper star of, now how do I pull back an operator? I'll have to write that whole formula. So if I, let's say, pull back E is a vector bundle on x, and then take the ith churn class, okay, and then operate it on F upper star alpha, where alpha is a class on x. This is the same as pull back by first operating E cap alpha. Okay. So well behaved with so it is well behaved with respect to flat pullbacks. Okay. Now what is the main ingredient here? The main ingredient here is that the first churn class is well behaved with respect to flat pullbacks, because in its essentially everything is defined in terms of first churn class of O1 by taking cap powers, cap product, and push forward. Okay. So again, this is writing diagrams, and also if you really do these two exercises, this will also be this functoriality will also be clear by using functoriality of first churn class. Okay. Now comes the non-trivial part. So this, of course, this is non-trivial, and then Whitney sum. Okay. So or that so which means that so given a short exact sequence of vector bundles E prime, E double prime, the total churn class of E is the product of total churn class of E prime dot total churn class of E double prime, where the total Chern class is the operator 1 plus C1 plus C2 and so on. This is not an operator of fixed degree like so, but it is an operator on whole of this direct sum A lower star x. Okay, so of course I can expand this and write Cn of E is summation I plus j equal to n Cj of E prime times Ci of E double prime. So this can be expanded. So this is a compact way of writing that same thing. So so this we will prove, and of course this last one is obvious that if E is a line bundle, then C1 of E cap product with the fundamental class is D, where so let's say if E is the line bundle which is OX of D, where D is a Cartier divisor. Okay, so if E is a line bundle given by the Cartier divisor, so now then the first Chern class is the class of that divisor itself in the correct. Okay, so these are the properties. So there are what are the non-trivial ones? This Whitney sum and this vanishing. Okay, so others also will take some writing down. I'm not saying that you may be able to look at it and oh, it's trivial. So but it is something which can be worked out as an exercise. Okay, so using what we have already done. So these two we will prove, and also we would like to, for example, put the Chern classes in our familiar formula, that if zeta is the first Chern class of O1, then that zeta to the power E plus 1 plus first Chern class times zeta to the power E, that expression is equal to 0. So that we would like to prove. So those all things we are going to do today. Okay, so now here is the main lemma that will help us. So this will help us to prove most of these things. So this says the following. So let E be a vector bundle such that it has this filtration where successive quotients are line bundles. So basically I have ER inside E and ER plus 1, sorry, R minus 1, and all the way up to E is 0, where E0 is the 0 vector bundle, such that if Li is Ei by Ei minus 1, then these are line bundles. Right, so I have a filtration of this vector bundles where successive quotients are line bundles. By splitting principle, we know that this is a very useful case. So this is not a very special case. I can reduce any, like if I want to check any equality in the Chow groups, I can reduce it to this case. So now suppose S is a section of E. Okay, I have a section of E, and let's say Z is the zero locus of this section. So Z is the zero locus of this section. I am not interested in the scheme structure of Z. So just take the zero locus as a closed subset, and because finally we are going to talk about Chow groups, and as Nitin said, it doesn't matter whether what scheme structure Z has. So but Z is a closed set. Let's look at all points where S vanishes. This is a closed subset. And then the claim is, okay, so this is a lemma maybe, so you'll see the utility in a while. So but let us first prove it. So C1, if I take the product of Chern classes of this Li, I equal to now 1 to R, okay, E is a rank R vector bundle in this case. If I take the product of these Chern classes, then the claim is that then, okay, so I should have said, then for all alpha in AK of X, okay, this is now an operator. So this operating on alpha is equal to beta, where beta is a class which is supported at Z. Okay, so let us let us spend some time understanding this. Unfortunately, I have run out of space, or let me write. So where beta is in A star of Z. Okay, let us, right now it may not be clear why such a thing is useful, but we'll see that in a minute. Let's understand the statement. If E has a filtration by subbundles where successive quotients are line bundles, this is our topological analog of E being direct sum of line bundles. And in that case, I have something to say about the product of this C1 of Li. Later on we'll see that this is going to be the top churn class of E. Later on we'll see that. Right now we don't know. Once we prove, once we proceed with the proof, we'll see that this is actually going to be the top churn class of E. But right now we don't know. So this product of C1 of Li, whatever it is, the claim is that it is supported on Z. What does it mean supported on Z? That whenever I act it on any alpha, the result is a cycle which is supported at Z. Which cycle and all I don't know, but it is supported at Z. Okay, so the product of the of this C1 of Li is something which is supported at Z. Now since this is an operator, I have to write it like this. For every alpha there exists beta. When we work with non-singular schemes, there I can actually say that this class is actually supported at Z as a cycle and so on. But right now this is the statement we want to make. So there is one very important. Is it any section? So for example, what happens when S is a zero section? I mean, it can have it is supported on X, which is a tautology. Every cycle is on X anyway, right? So if S is a zero section, this is not giving us any information.
But this statement is in sections of dependent on the section, right? What section you are
Yes. So yeah, so I understand where your questions are coming from. This product of C1 Li has nothing to do with sections, okay? But this S is still playing. So for example, for different sections, I'll have different Z, right? And then I'm saying that, okay, this is equal to beta where beta is coming from that Z, which is not a contradiction. So like a cycle on one Z1 can be equivalent to a cycle supported at another Z2, right? So that is not, there is no contradiction here. So given a section, I know that the product of these C1 of Li has to be supported at the zero locus of that section. And one very important case for us is when we have a nowhere vanishing section of E. Okay, if suppose the zero locus of E is empty, then what do we know? Then we know that the product of C1 Li is 0, right? So that is the most important case for us right now. Okay, so and remember, this product of C1 Li is going to be the top churn class. We will see in a moment why, not in a moment, but in maybe 20 minutes. So correct, correct. So it has to be, so what I mean is beta is I lower star of something in, so yes, this is a bit sloppily written. So with the cost of, by introducing more notation, maybe I should write that. So given us, there is a cycle on Z such that its push forward is equal to this. That is the precise statement. Okay, but let us do one thing. Let us assume this and see how this is useful. So it will be more interesting to prove it once we know how it is useful. Okay, so let's assume that lemma. Okay, so now let's say so now here is a theorem. Okay, so if E has a filtration, so as has a filtration, ER minus 1, so same as notation, same as in the lemma, and LIR same. Okay, I could have just written that notation same as in so, but anyway, too late. So E equal to so Li are these line bundles, so these are line bundles. Then the claim is that the total churn class of E, C of E, okay, the total churn class. So this is 1 plus C1 plus C2 up to, I don't even know up to where, because I don't know it, the churn classes vanish after rank. But the claim is that this is equal to product of 1 plus C1 Li. r equal to 1 to r. This is equal to now you see, if for example we knew this property of Chern classes, this Whitney sum, okay, then I know that the total Chern class of E is the product of total Chern class of the line bundles, right? Then I know that, okay. So the total Chern class of a line bundle is yeah, 1 plus the first Chern class, okay. Yeah, so here is the question: why does the second Chern class of a line bundle vanish? Okay, this again I am going to leave as an exercise. So there you will have to take projective bundle of the line bundle, which is just X itself, and just basically work out the definitions. So it's an interesting exercise to check that the total Chern class of a line bundle is 1 plus C1 of Li using our definition of Segre classes and Chern classes. Okay, so once if I know that the Whitney sum is holds, then this formula must be true. Okay. Conversely, by splitting principle, this formula we will deduce Whitney sum. So that I will indicate how. But if Whitney, right? Is that clear? Because see, once I have this filtration, so now that Whitney sum says something about short exact sequence, right? So like for example, if I have this ER minus 1 to E, which is equal to ER. Sorry, this last thing is equal to E. Okay, ER which is equal to E, and ER minus 2. This is a short exact sequence. So the total Chern class of this is the total Chern class of LR, because this is ER modulo ER minus 1. Right? This quotient is, sorry, ER and this has to be the quotient, and R minus 1. So the total Chern class of ER is the total Chern class of LR times ER minus 1. Now repeat inductively. So you will finally get the total Chern class of E is the product of all these total Chern class of the line bundles, provided we know this. Right now we don't know this. Okay, so this is a step towards proving that, and much more. So I'm just so in any case, this is a formula that we want to prove. Another thing that we will achieve after proving this is this vanishing. Automatically the Chern classes will vanish after the rank for this situation. When the vector bundles has a filtration where successive quotients are line bundles, then the Chern class will vanish after the rank. But then by splitting principle, it vanishes for every vector bundle, because I can always pull back and the cohomology injects, right? So that is so this formula will actually solve most of the things for us. So let us first prove it, and then we'll also discuss whatever I said right now verbally. We'll write it down. Yeah. So why is such a thing true? Because you see now look at this projectivized bundle of E. This is on X. This is pi. Now the pullback of E has a tautological subbundle, right? So there is this O minus 1, which is a subbundle of the pullback of E. It is a subbundle in the sense the quotient is again a vector bundle. Okay, so now what I can do is I can tensor. So let's say this is the inclusion. Okay, so this is the inclusion. Now I tensor with O1. Okay, so I get O sitting inside the pullback of E tensor with O1, right? I get pullback of E tensor with O1, and I have O sitting as a sub. So there is a trivial line bundle which is a sub bundle of this. So any map from O to a vector bundle gives a section. Why is this nowhere vanishing? Huh? No, wrong reason. Quotient is a vector bundle is important. Okay, so the quotient is a vector bundle. So therefore, so again, so these small things have to be worked out, and so these are all small exercises. So this gives a nowhere vanishing. So therefore, we have a nowhere vanishing section. Nowhere vanishing is not the same as non-vanishing. Okay, so nowhere vanishing section of pi upper star E tensor with O1. Okay, now I want to apply this lemma. There is a nowhere vanishing section. So what happens to the product of the Chern classes of which appear in this associated or the successive quotients? You see, E has a filtration. I can tensor this whole thing by O1, and E has a filtration. So pi upper star E has a filtration, right? I can pull back, and where successive quotients will be line bundles, I can tensor that whole thing with O1. So that also has a filtration, where the original filtration tensored by O1, and the successive quotients will be line bundles. What will be those line bundles? Li tensor with O1, right? So this has a filtration where successive quotients are Li tensor with O1. So therefore, by this lemma, okay, let's give some names, star. Okay, so by lemma star, I know that product of the first Chern class of line bundles which appear in the successive quotients, that is 0. But in this case, the successive quotients line bundles are pi upper star of Li tensor with O1. This is 0. This is by this lemma. Let's make sure that this is clear. So this lemma, I am applying it to pi upper star E tensor with O1. And so the line bundle quotients are pi upper star Li tensor with O1. And so the product of the first Chern class of line bundles, now those line bundles are pi upper star Li tensor with O1, that is 0, because it capped with any alpha is cycle supported on, in this case, empty set. So therefore this has to be 0. Okay. So this is 0. But what is first Chern class of tensor product of line bundles? It's addition of the Chern classes, addition as operators. Okay. So therefore, if zeta is the first Chern class of O1, then we have product of C1 of Li or pi upper star Li plus zeta, this is equal to 0, right? This is what we have. Yeah, so let us expand this product as so E has rank R, so there are exactly R line bundles here. So then I get zeta to the power R plus, now there will be some coefficients. So let me comment on the coefficients in a minute. So sigma tilde of 1 zeta to the power R minus 1 plus sigma R tilde equal to 0, where sigma 1 of where sigma 1 is the sum of all C1 of Li. So it's like the first symmetric function in C1 of Li. Take the sum of all C1 of Li. Sigma 2 is so sum of pairwise products, right? So whatever appears in the expansion, how will this expansion look like? Zeta plus, let's say, C1 of Li. So of course here it's pi upper star. So therefore these will be, so sigma n, let me just write down. So sigma I is the ith elementary symmetric polynomial in C1 of Li. So these are R many, and I have to take elementary series. So first one is the sum, second one is the pairwise sum of the pairwise products, and the third one is the sum of no, this is sigma I, and sigma tilde will be the pullback. Okay, so and sigma I tilde is pi upper star of sigma I. Okay, so that is the notation. So this is an equation that we have. Looks very familiar, like our original topological, like when we define Chern classes in topology. Okay, so the sigma I tilde are going to be the Chern classes. Okay, so yeah, so therefore, so I have this. Now I can, so I will multiply this by I. So therefore, for all I have zeta to the power r plus I, or r is the rank, so r plus I minus 1. So multiply this by I minus 1. I get this plus sigma 1 tilde zeta to the power r plus I minus 2 plus dot dot dot, and the end product will be sigma tilde of r zeta to the power I minus 1, because I have multiplied by I minus 1. Okay, so I have this, and then from this you can actually check that this just means that 1 plus sigma 1 tilde t plus sigma 2 tilde t plus dot 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 up to sigma r tilde t, this times the total Segre class. So 1 plus S1 t plus, this is the total Segre class, this is equal to 1. Okay, so let me comment why this is true. Because what is the what is the total Segre class? So maybe, yeah, one more step is needed. So claim. This is the claim. Why this claim is true? Because once I have this equation, let's pull back a class from X, cap it with this operator, and then push forward. Okay, let's see. Then that will be of course 0. So therefore, for all alpha, we have zeta r plus I minus 1 cap pullback of alpha. Yeah. Sorry. Plus dot 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 sigma r tilde times zeta I minus 1 cap pullback of alpha, and push forward of this equal to 0. See, once I have some operator equal to 0, I can apply that operator. So pull back alpha, apply that operator and push forward, I get 0, right? So, but you see, what is this? Now separate the sum. What is this term? I am pulling back a class, zeta is the class of O1, I am taking some power of that, right? And then pushing forward. So this is the definition of Segre class. Which Segre class? R is the rank, so it is the ith Segre class, right? So I get Si plus sigma 1 Si minus 1 plus dot 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 up to sigma, sorry, sigma r Si minus r, this equal to 0. Okay, so now you'll say, this is I minus 1. In the projective bundle, wasn't our rank E plus 1? So therefore I have to use R minus 1 here, and therefore this is Si. So we have this equation. Again, elementary exercise. This equation is equivalent to saying that this product equal to 1, because of course 1 times 1 is 1, but all the coefficients of t are, these are basically all, this is basically the coefficient of t to the power I. So all the power coefficients of t to the power I vanish, so this product becomes 1. So this is the formal inverse of this. Okay, so therefore these are I mean sigma is or? Yes, so this is sigma tilde above, sorry, here I mean sigma sigma i's. Okay, here I mean sigma i's, because once I push forward, I push forward of this by projection formula is multiplying below. Okay, so yeah, here I mean sigma i's, correct. So therefore we have this formal inverse. Now there is of course a small step left to you, which is this checking this elementary thing, that this gives this formal inverse. And now you have this, this means that the sigma i's are our Chern classes, because there is only one formal inverse. You can explicitly write down the formula. So therefore Therefore, sigma I is equal to Ci of E, the first ith Chern class of E. It has to be. But so this is the elementary ith symmetric function in C1 of Li, right? Okay, so this we have, and therefore we obtain. So therefore, Ci of E equal to 0 for all I greater than rank. So this we have now, right? Because there is nothing more than R here, right? The formal inverse only requires R terms. So this is what about Whitney sum? So now let's prove Whitney sum. So now if E prime, E double prime is a short exact sequence, okay, then we want to show that C of E is equal to C of E prime dot C of E double prime. This is what we want to show, okay. I want to say, without loss of generality, we can assume that all these vector bundles have a filtration where successive quotients are line bundles. Why can we assume that? Because we want to check some equality in the Chow group, and by splitting principle, I can find a space where the pullback of all these vector bundles have a filtration, line bundle filtration, let's call it, and then there, if I prove this equality, it's good enough, because Chern classes behave well with respect to pullbacks, and right. So without loss of generality, so or like let's say by splitting principle, we may assume okay, so I'm going to write like this on this board, that assume that there exists a filtration of, I also want a compatible filtration, which means I want I want a filtration of E where E prime also occurs. So this is, so basically there exists a filtration of E. So let's say E0 contained in E1 contained in dot 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 EM, where this EM becomes E prime, okay, then contained in dot 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 E, such that, so let's say this is ER, and then contained in this is ER is equal to E, okay. I want a filtration where one of them becomes E prime. So how do I do this? I first find a filtration of E double prime, pull it back to E, and then find a filtration of E double. Like I'll have to do this two morphisms. Again, these details are best left as exercise. So I have such a filtration, and successive quotients are line bundles. So what is the total Chern class of E prime? That is equal to product of 1 plus C1 of Li, where I goes up to M, right, where I goes up to M, I equal to 1 to M. But you see, E mod EM is E mod E prime, which is isomorphic to E double prime. So what is the filter? What are the line bundles which occur as successive quotients for E double prime? They are all the Li's where I is greater than M, right? So C of E double prime is product I greater than M of 1 plus C1 Li, and of course the product of this is product of 1 plus C1 Li, so therefore C of E prime times C of E double prime is equal to C of E, right, because the Chern class of E is also the product of this 1 plus C1 Li, right. So therefore we have this, and we also get this familiar formula in topology, that zeta r plus, now there is no minus 1 to the power something, because that time I had taken first Chern class of O minus 1. Here zeta is first Chern class of O1, so there is no minus 1 powers of minus 1 needed. Okay, so
this flag, right? That is only critics for bundles with this tag is not inside U and that, but how to get it for bigger than 1?
No, that's what I said, by splitting principle. So therefore what we do is, given a general bundles, I find a morphism y to x where the pullback of these bundles have this filtration, and the map on the Chow groups is injective, the pullback map. This is possible by splitting principle.
This is an equality in the Chow group of E, right?
This equality is in the Chow group of the pullback, but this equality is also this is an element. This minus this is an element below. I want to show its pullback is 0. It is 0.
I am talking about this relation, that the relation is so sigma and that is sigma. So this thing we have to show for any.
Oh yeah. Because there also I use splitting principle. Like I have projective bundle of E, then I find Y and I pull back the bundle. The O1 will pull back, and this splitting, okay, you have to show that Y2X split is the Chow group is injective, then this is also injective. Okay, maybe Chow group calculation of the projective bundle is required for that. So maybe that that will be finished after I finish a few more parts. Yeah, correct. So or perhaps there is also maybe so anyway we are going to do something which will address that question. Okay, so this proves that 3.2 completely modulo this lemma. So let us see why this lemma is true. So proof of lemma star. Okay, now the section of E induces a section of any quotient of E, right? So I have this E maps to LR, and the quotient is ER minus 1, right? So we are going to do this by induction on the rank of by the rank of E. So E maps to LR. So let's say S bar is the section of E LR induced by S. S bar is the section of LR induced by S, right? So what can you say about 0 locus of S and 0 locus of S bar? I have some section here, then vanishing locus of that, and as compared to vanishing locus of the induced section of LR. What can you say? Which containment? Second one is possibly bigger, right? So 0 locus of S bar clearly contains 0 locus of S. Okay. Now if I cap anything with alpha, so now I take I'm going to write this product, separate the LR factor first. Okay, so what happens if I do C1 of LR cap alpha? You see, LR now has a section S, so it's a pseudo line bundle, right? It is going to vanish. It is going to be a non-vanishing section outside Z of S bar. Right? So LR comma Z, let me call this Z bar. Okay? So Z bar comma S bar. This is a pseudo line bundle, pseudo divisor, and the support of the pseudo divisor is Z bar, right? Support of this pseudo divisor is Z bar. Therefore, if I do C1 of LR cap alpha, this is a cycle which is coming from A k minus 1 of the support of the pseudo divisor, which is Z bar. Okay, again to be precise, it is push forward of the cycle. Okay, so of Z bar. Right, this cap product. So this is where we use that finer thing, that D dot alpha actually is a well-defined cycle class in the support of that divisor. Okay, so this is where it has been used. So this is actually supported here. Okay, so therefore, so now enough to show that on Z bar. Okay, now. On Z bar, product of C1 of Li, now LR has been taken care of. I equal to 1 to R minus 1. This cap alpha no, sorry, this I want to give some name. Let's call it alpha r, which is in this. So this cap alpha r, it is enough to show that this belongs to a cycle in Z. Z is my original zero locus of the section. But what happens is that on Z bar, okay, so now let us look at this exact sequence. So I have this exact sequence. I have this section here which goes to S bar. If I restrict this short exact sequence of vector bundles on Z bar, what happens is this section S goes to 0, section of LR restricted to Z bar. So we have this exact sequence ER restricted to Z bar, then LR restricted to Z bar 0, and ER minus 1 restricted to Z bar. So I restrict the whole thing to Z bar, and now of course the section also restricts the original section. Let me continue to call it S, but now LR, it maps to 0 section because I am only looking at Z bar now, where S bar anyway vanishes, right? So this section goes to 0 section here on Z bar, not on whole of X, but I am restricting my attention to Z bar now. So this goes to 0, therefore it induces a section on E of ER minus 1. So therefore by induction I am done now, and that section, the zero locus, is exactly Z. Okay, so therefore so this is a sort of an inductive proof. Of course, first step of induction is this line bundle and contained in support that case. So therefore so now S induces or a section of ER minus 1 restricted to Z bar, because on Z bar it goes to a 0 section of LR, therefore it comes from ER minus 1. And then the same lemma, by induction it holds on Z bar, X equal to Z bar, and therefore I am done. Okay, so therefore by induction we are done. So we have finished proving all the properties of Church classes that we would like. Now what I would like to do is, except possibly this equation that will come in a minute, or by the end of this lecture, not maybe immediately, after we prove the projective bundle formula. So what remains to do is to calculate the Chow groups of projectivization of a vector bundle. So that is one of the things that remains.
One small comment.
Yeah.
Smooth projective flow, this hypothesis is always satisfied. Every vector bundle has a filtration, so the successive quotient are line.
Yes. On smooth, yeah. So there correct. So I don't know. Does is this statement? Maybe this is a good discussion session topic. Okay. So now. So there are a few things. So the goal now is to calculate so we would like to say something like the Chow group, the Chow ring of the projectivized bundle is a free module of the Chow ring below by 1 zeta z, but there is no Chow ring. We have not defined Chow ring, and that only exists for regular schemes anyway. So what we are going to prove is something analogous, but before that, so goal is to calculate Chow groups of projectivization of E in terms of course Chow groups of the base space, so X. So like it will be a free, it will be direct sum of Chow groups of the base, like suitably shifted. So we will write down the exact formula. So but before that, so here is lemma, okay, so or theorem. Okay, so this I think is 1.9 in the book, in case you want to refer back, and I think Nitin is also going to discuss this. So let E to X be an AN bundle. What does this mean? So it means that, so that is there exists an open set, that is locally E is isomorphic to or let's say E restricted to U is isomorphic to U cross AN, affine space. I am not interested in vector space structure right now. So there is an open cover over which E is the base cross the affine space. So this is an AN bundle. Of course, an example is a vector bundle. Okay, so that is the prime example we have in mind. So for such a thing, we will show that. So the theorem says that the map from AK of X to, and let's say this is N. So the pullback map will go from AKX to AK plus N of E. This is surjective. Okay, this is maybe best, initially I would like to call it a lemma, because this is what we would like to say is that this is actually an isomorphism for a vector bundle, but right now for this affine bundle we'll first prove surjectivity. So okay, so proof uses Noetherian induction. I think Nitin is going to discuss that in great detail. I'm going to just indicate whatever is just necessary for the proof. So the point is that there exists an U in X such that E restricted to U is isomorphic to U cross AN. Okay, actually it is true for an open cover, but select one open subset. Okay, and then let Y be equal to X minus of U. This is the closed subset. Okay, and then we have a short exact sequence AK of Y mapping to, so right exact sequence, yes, AK of Y mapping to AK of X mapping to AK of U. This was the slide number 10 of today's first lecture, right? So we have this right exact sequence. Similarly, I have AK of E restricted to Y, so which is the fiber product of E and Y over X. That is again an affine bundle, AN bundle on Y. Okay, so so I have this AK of E and AK of EU. Okay, so arrow is up, so arrow goes up in the upward direction. These are the pullbacks. I'm going to call all these maps pi upper star. Okay. So now the idea is that now Y is a smaller closed subset. So I would like to say by induction we know the result on Y. Okay, and so it is enough to prove it for U. That is what Noetherian induction is. But what does it actually mean? The point is I will first take care of Y. So I'll replace X by Y. So I have replaced X by a smaller scheme. Okay, and so on until so there is any descending sequence of closed subsets of X stabilizes, right? So therefore this cannot go on forever. So the point is it's enough to show it for this open set, because finally I'll be left with something where I cannot find a closed subset, and that will be U, right? So I have, so we assume, so by Noetherian induction, so I'm going to leave this bit vague because I think you will explain this in great detail. So this is a good opportunity for you to think, and then so by Noetherian induction, enough to prove that this arrow is surjective. Okay, so again here I have to point out one diagram chasing exercise. If this is surjective and this is surjective, then this is surjective. Okay, that is a simple exercise, maybe 5 lemma or something, but maybe more simpler than that. So by Noetherian induction, it is enough to prove that this map is surjective. Okay, so now this Noetherian induction has to be understood, because how do I take care of Y? Similarly, I take care of Y because in Y I find an open set and so on. But this cannot go on forever, because descending sequence of closed subsets of X can only be a finite sequence, and that is what Noetherian induction is about. So enough to prove for this pi upper star, this U. So therefore without loss of generality, so on U what happens is I know that E is U cross AN. Okay, so on so therefore without loss of generality we can assume that E is actually X cross AN. But to show surjectivity I can E is x cross an is an a1 bundle on x cross an minus 1, and an minus 1 is an a1 bundle on an minus 2, and so on. So it's enough to prove this for n equal to 1. So again, without loss of generality, n equal to 1. This is the reduction. Okay, n equal to 1. And okay, so I am a bit short on time. So what I will do is some of this thing I think you will.
I'll do all of it.
I'll just okay. So let me. So yeah. So for x cross a1. So let me just finish it at some logical point. So on x. So basically I have to show that pi upper star is surjective. Map pi upper star on chow group of x to chow groups of x cross a1 is surjective. This part will be done in Nitin's lecture. Not because it is difficult, because I have to finish the projective bundle formula, and I think he will explain this nodal induction much more nicely. So therefore let me assume this. So this is the reduction we saw, but this remains to be proved. Okay, so in fact yeah, okay, so let me say only this much. So now let us go to the case when we have a vector bundle. Okay, so theorem. So this is the last theorem that I want to prove today. So E is a vector bundle of rank, let's say E equal to E plus 1 on X. Then the claim is that pi upper star from ak of x to ak plus E plus 1 of, or let me just say a star of x to a star of E is an isomorphism. The pullback is an isomorphism. By the way, I forgot to point out one important corollary of this thing. This shows that the chow group of affine space is trivial, because the pullback map from the point to an is surjective, and sorry, they are trivial except for the topmost. Okay, so therefore so that is one corollary. So here we are saying something stronger. We are saying that for any vector bundle, the chow groups of the vector bundle and the chow groups of the base space are isomorphic. Not just that this map is surjective. The surjectivity has been stated in that lemma, and modulo this part it has been proved. So second, we want to say something about the projectivization of E. Okay, so if beta is a class in AK of P of E, beta is a class in the beta is a kth class in the projectivization of E, then beta can be uniquely written as beta equal to summation I equal to 0 to E, okay, C1 of O1 to the power I cap P upper star alpha I, where alpha I are in the chow groups of the base space. Of course, they have to be the correct dimension so that the sum I get is exactly K. Okay, so I am not right. So is this clear? So so that is exactly what we are saying. Is this clear? What? Let me. This is pi. Yeah, sorry, pi. So yeah, pi up. So I'm going to write P upper star. So P is the projection from, because now we have E to X and we also have projectivized bundle of E to X. This is going to be called as P. Okay, so now there are two projections. So let us call this as P. Right. So what we are saying is that take any class above. It can be written as a pullback of class below plus C1 times a pullback of class below. Of course, now the second class will be in right. So is this statement clear? This actually shows that okay. So let us start with the proof, and maybe the proof will make the statement clearer. So proof. Define theta E a map from direct sum of I equal to 1 to, so how many, I need I equal to 0 to E, right? So I equal to 0 to E of A star of X to A star of P of E, okay, by sending alpha 0 up to alpha E to that type of a sum. So I would like to write it as alpha 0 plus zeta times alpha pullback of alpha 1 times alpha 1 plus dot dot dot. But then you see this, I have to write cap product. So let's say so I want to, okay, so maybe let me write this zeta E plus so alpha 1 alpha naught plus zeta times alpha 1 up to zeta to the power E. Okay, so this goes to alpha naught plus alpha 1 zeta plus alpha 2 zeta square plus zeta alpha E zeta to the power E, where zeta is C1 of O1. Okay, so now this is like saying that this is a free module generated by 1 zeta, zeta square and zeta to the power E, except that these zeta are first Chern class of O1. Right now they are operators, so I have to write this cap product. Okay, so that is so therefore I have to write cap here. This cap alpha E, sorry, this cap alpha E alpha 2, yeah, I think I should write this again, alpha naught plus zeta cap alpha 1 plus dot 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 zeta to the power E cap alpha E. This is the map. Of course not alpha I have to pull back alpha I and then cap it. That is making it very notation heavy. So that, let me be a sloppy and ignore this P upper star. Actually I have to do P upper star here. Okay, so we want to show that theta is an isomorphism. So we will first show that theta E is surjective. Theta is surjective. So again, by Noetherian induction, so this map is such that it is well behaved with respect to restriction to open and closed subsets. So therefore, by Noetherian induction, by Noetherian induction argument as before, right here on this board. So induction as before, we may assume that the bundle is trivial. So I can restrict it to an open set. And only surjectivity I can handle it like that, because you see, if these two are isomorphisms, because this is not exact here, I am not sure if this will be an isomorphism. So but surjectivity, yes. As before, we can assume that E is trivial. Okay, so therefore projectivization of E is actually X cross Pn. Again, I want to say we can assume n equal to 1, but here it is a little bit complicated, because X cross Pn is not a P1 bundle over X cross Pn minus 1. Okay, so like Pn is not P1 cross Pn minus 1. So therefore a little bit more work. This works what?
On any PN bundle, not necessarily for collective space bundle.
The surjectivity? Yes. But for any PN bundle, I don't know what is O1.
Okay.
Right, O1, I know if there is Proj, then there is O1. If I just have locally PN, I don't know if there will be an O1. Okay. So the idea is that, so by induction, so let F be equal to E direct sum OX. Okay, so F is trivial, E is also trivial, and but F has rank one more. So enough to prove, so enough to show theta F is surjective, assuming theta E is. Okay, so this is by induction because I can do I can increase the rank one at a time. So I assume the result for theta for E, and then I prove it for F. And then so now here let P be equal to proj of E, Q be equal to proj of F, and then you see proj of E sits inside proj of F. So P sits as a closed subset of Q. Okay, so in fact fiber wise, if you see, this sits as Pn minus 1 inside Pn, right? So in fact both E and F are trivial. So actually this is equal to x cross Pn minus 1 and this is equal to x cross Pn. Okay, so whatever statements I say, so it is you can just check it for project. So P sits inside Q and the complement is x cross An. So the complement is actually E. So this is J. The complement is the vector bundle E. So projectivization of E direct sum OX is actually a projective completion of this space, like in. So is this clear? So because this is x cross Pn, this is x cross Pn minus 1. If I remove this from this, I get x cross An, which is naturally equal to E, right? And I have these maps. So this is my map. Now I'm going to call it Q to X. This was pi, right? And this was P. These are the maps, and this is, let's say, I. So there is one observation I want to make. So lemma that for any alpha in which is a class on X, if I pull back by this P upper star alpha and then push forward, how does it compare to Q upper star alpha? So is this equal to Q upper star alpha? It is not, like it is not, because you see, so the exact formula is this is equal to Q upper star alpha. This is actually C1 of O1, OF1 to be precise, cap with Q upper star alpha. Okay, we want to prove this lemma. So let us see why this is true. Proof again. Something that sort of these arguments we have done before. So without loss of generality, alpha is the class of an irreducible variety V, right? And then the point is that if you look at, so what is the class Q upper star alpha? This is the class V cross Pn, right? I just take the inverse image, any of anything below. It's like the projective bundle over that V, right? And C1 of O1 is the line bundle O1 here, right? If I cap it with C1 of O1, I get V cross Pn minus 1, precisely this. So therefore C1 of O1 cap Q upper star alpha is V cross Pn minus 1, right? So basically this is equal to P the class defined by P inverse of V. And but this is exactly equal to P upper star alpha, which is the class defined by P inverse of V, now considered as X, right? So therefore we have this. So if I pull back by P and push forward, that is the same as pulling back by Q, but I have to, here I have a class supported on P. This pullback is not supported on P. I have to intersect it with the first churn class. Okay, so this is the claim. Okay, so now once we have this, now let us use surjectivity. This surjectivity we already know that pi upper star is surjectivity from X to E. The proof will be completed in Nitin's lectures. So let's take a class beta in A star of Q. Okay, then I know that J upper star of beta. This is a class on E. I know that any class on E is a pullback from X because pi upper star is surjective, right? So therefore this J star of beta is equal to pi upper star of alpha for some class alpha. So, so therefore, if I look at beta minus q upper star alpha, okay, so pulling back by pi is the same as pulling back by q and then pulling back by j, right? Because so therefore this, the j star of this is equal to 0. Okay, because I have a class here, I go here, I know it's a pullback, I adjust this class by this pullback and then I get something which maps to 0 here. Okay, so so therefore, so this is equal to 0. Therefore, by that right exact sequence that we have, because this is a closed set and E is the complement of that. So we know that beta minus q upper star alpha is equal to I lower star of some class gamma in P. So where gamma is in A star of P. Yeah, so gamma is in A star of P. But I know the theorem that this theta E is surjective. So any element gamma in A star of P, so gamma can be written as O1 C1 of O1 of E, okay, to the power, so summation I equal to 0 to E minus 1 now. So to the power I cap P upper star alpha I. Okay, any gamma can be written like this. Okay, so too much of notation and symbols unfortunately are appearing, but yeah, so I hope. So actually the idea is clear. So what we want is, we know that this is direct sum of A star x, and but that map is also this theta E, so or at least the map is surjective. So therefore gamma can be written like this. Now when I push forward gamma, I am going to use that lemma. Okay, so push forward of gamma is actually push forward.
P star is surjective.
Theta E is surjective. P star is not claimed to be surjective at all. Like the cohomology above will be like direct sum of. So push forward of gamma is I equal to 0 to E minus 1, and I have to push forward those classes. So I lower star, sorry, this is I lower star, not P lower star of gamma. I lower star of C1 of O1 of E to the power I, sorry, I and this I, maybe this should be L. Okay, so L cap P upper star alpha I. Now what I am going to do is first use projection formula, because O1 of OE1 is the pullback of OF1. Okay, so I upper star of OF1 is, sorry, OQ1. So Q is OP1. So therefore this becomes summation L equal to 0 to E minus 1. This by projection formula it comes out as first Chern class on Q. Unfortunately I erased the diagram. So I have Q, P, this is I, this is J, E and X. Okay, so Q and P, this I need pi. Okay, so therefore this becomes L equal to 0 to 1. Yeah, so what I'm afraid is in writing so much, I may not be anyway conveying, so maybe at this point I'll just say exercise. Okay, so because, and verbally do it. The point is, I want to write a cohomology class as sum of elements alpha naught plus zeta to the power alpha 1 and something. Okay, so beta minus something which is pullback from below can be written as push forward of a class. Here it can be written as alpha naught plus zeta times alpha 1 and dot dot dot. And when I push forward, because of this lemma, I multiply that whole thing by one more power of zeta. Okay, so one more power of zeta. So all the terms here, the result of this push forward is I multiply one more power of zeta, and this is the 0th power of zeta, and therefore beta will be equal to that. So that is as good as writing this whole messy equation, because the underlying idea is not difficult. So therefore I will leave this this, okay, so by projection formula and this lemma, let me say 2, okay, so because that was the first lemma that we, we get surjectivity of theta e, okay, we get surjectivity of theta e. So there is some exercise part here. I am not claiming I wrote down all the details, but actually it is a very simple concept with too much of heavy notation, so better you do it. Huh? Yeah, I mean, okay, theta f is surjective, correct. For E, then we reduce it to f. So therefore theta is surjective for every vector bundle E. That is what I want to say. Okay. So now let us finish by showing that theta is injective. So injectivity of theta. Okay, now my f is not there. I am just taking one projectivization of one of the e's, and yeah. So suppose so injectivity of B is like uniqueness of that expression. So every beta can be written in the following way, and if these coefficients alpha are unique, that is what injectivity means. Suppose not. So suppose not, which means that there is a linear combination of these alpha i's where alpha i's are non-zero but beta becomes 0. Okay, so suppose not. So 0 equal to beta is equal to summation. Now let me write zeta for C1 of ONs, zeta to the power I cap P upper star alpha I equal to 0 to E. Suppose this is the situation. Then I am going to look at the largest I for which this alpha I is non-zero. So let L be the largest I such that alpha I is non-zero. Okay. Of course, if we want to show alpha I is 0 for every I. So if not, then there is some largest integer for which alpha I is not 0. So alpha L is non-zero. So what I do is I multiply this whole thing by, so multiply by zeta to the power E minus L, I think. Yeah, E minus L. And push forward. So look at P lower star of zeta to the power E minus L cap beta. How does this look like? So now I have to split and split each term. Okay, so now L is the largest term. There is nothing more than L. Oops, this, or maybe let me erase this. So let's look at the Lth term. So it will be, this will be the summation of, this will be summation P lower star. Now I have multiplied by zeta E minus L. So it will be zeta E minus L plus I, okay, plus I, L plus I cap P lower star of alpha. Okay. Now you have to check that for, so this is actually, this is Segre class acting on alpha i's. Which Segre class you have to keep track of? Except L, it's going to be the negative Segre classes, right? So this is going to be S naught of, S naught cap alpha L, okay, plus some summation, I don't want to write the exact indices, SI cap alpha I, where I is negative. Okay, so there is only one of this term will be S naught, the remaining will be the negative Segre classes. So we have already shown that negative Segre classes are 0, so this term will be 0, and S naught cap any class is that that thing alpha L itself. So this will be alpha L, right? This will be alpha L. So therefore, if I push forward P lower star of zeta E minus L cap beta, I get alpha L, but beta was 0. Right, beta was 0, and therefore alpha L is 0, but I said alpha L is non-zero, right? So because L was the integer where alpha, so which means all the alpha have to be 0. I cannot choose a non-zero alpha L. So that shows uniqueness. So therefore theta is isomorphism. So we get that the Chow groups of the projectivization are actually direct sum of Chow groups below, and there is this precise map using the first Chern class, this theta E. Okay, so now let us show, so now it remains to show that pi upper star is an isomorphism. Okay, so on injective, we have already shown surjective, or it will be shown to be surjective, so is injective. Okay, and now suppose not. So suppose there exists alpha in A star of x such that pi upper star of alpha is equal to 0. Then what happens? So again look at the diagram that I erased. Sorry. So Q P E. Okay, so if I want to prove pi upper star, I'll take Q to be projectivization of E direct sum OX, and this diagram. Okay, so this was the diagram. This was J Q pi. Okay, so then so therefore J upper star of Q upper star of alpha equal to 0, which means that this Q upper star of alpha comes from P. So therefore Q upper star of alpha is equal to I lower star of something which comes from I lower star of some class beta. Okay, some class beta, but so where beta is in the Chow group of P, but in the Chow group of P, this beta will look like, so I lower star, it will look like zeta, so summation of alpha naught, so alpha naught plus alpha 1 zeta plus alpha E minus 1 zeta E minus 1. Any class in this, because now we have proved that theta is an isomorphism, or in fact surjective is enough. So then any class here beta looks like this. When I apply I lower star, what happens is I end up multiplying this whole thing by the first Chern class, which is zeta. I am slightly confusing zeta, the first Chern class of O1 on Q and O1 on P, but by projection formula, this confusion is, so this is not a problem. So therefore this will be equal to alpha naught zeta plus alpha 1 zeta square plus dot 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 alpha E minus 1 zeta to the power E. Right? Actually, I have to pull back here, Q upper star. So, but you see some expression where zetas are positive is equal to something where zetas are, the zeta to the power is 0. That contradicts uniqueness of this expression. Right? So, I get a linear combination which is 0. So, therefore, this contradicts injectivity of beta for this vector bundle F. So that shows that for a vector bundle this pullback map is an isomorphism. So we are done. So I'll just make one more definition. So and then I stop. So if E over X is a vector bundle, we just showed that pi upper star from AK of X to AK plus R, let's say vector bundle of rank R, is of E. This is an isomorphism, and therefore I have an inverse. Every K plus R cycle is a pullback from a K cycle. So therefore I have maps S from AK of X, AK of E to AK minus R. So I have replaced K by K plus R of X, which is S equal to pi upper star inverse of this map, because these are isomorphisms. So let me put K minus R and K here. So for all K I have such isomorphisms. Their inverses are called Giessen maps for vector bundles. So this is called Giessen maps for vector bundles. So this is like pullback along the zero section, if you like. They are defined by first showing the pullback is an isomorphism, but you can think of it as that you can pull back along the zero section of that vector bundle. So this is yeah. So this is that. So that is all. So I understand that in the end the calculations were a bit fast, but this is theorem 3.3 of Fulton. So it's hardly 1.5 page. So some of these details, like if they're not clear, I hope the overall idea is clear. So you can refer to that 3.3 proof and fill in some of the things that I did verbally. Okay, so I'm done for.